So, hi sir, this is Emily, and I'm going to talk about the optimization question. So first, I'm going to read through the whole question and gather the information. So after reading it, I find out that the cost of the sides and top is $3 per meter square, and for the bottom is $5 per meter square. So the question want me to find the dimensions of the rectangular box and to maximize the volume, which means the volume is what I'm trying to optimize. So the constant number is the total cost of the material of it is $600. So now I can draw my diagram of the closed rectangular box with a square base here. So which means the length and the width should be the same. So I would let L to be both of my length and the width of the rectangular box, and H to be the height of the rectangular box. So I'm going to find my constraint equation here, which means I'm going to find the equation for the constant number for the total material costs for $600. So it means that we had to find the surface area of this rectangular box, which means it has 4 sides and 1 top, and it has 2 times to $3 per meter square. And for the bottom is L squared and times $5 per meter square, and to get my equation here. So what I need is to let my L to be the independent variable and H to be the dependent variable. And step 4 is to find the volume of it, because the volume is what I'm trying to optimize. So volume exactly to consider. So what it is the length times width times height. So it's L squared times H. So now I'm going to combine this 3 and 4 together here and to get my final equation, which means that I just substitute the H to this equation here. And after simplifying, I get this final equation here. So now means step 6 to get the domain of this question. And as we know, dimension can now be negative. So the length should be bigger than 0, and the H should be also bigger than 0, as well as the width. So here I will let this equation here to bigger than 0, and we know that L should be approximately equals to 8.66, and after I use the sign chart, I get the domain here. Although it's really reasonable for real life, but I want to use the EVT, the extreme volume theorem, so I have to let both sides as well to equal them, because I want a closed interval here. But before I do that, I will put 0 and 8.66 back to the equation here to see if it's reasonable to equals to both of sides. So after I do this, it's really reasonable, and I can use this as my final domain here. So for step 7, I'm going to find the derivative of the equation here. So after I do this, simplified, and then find this final equation here. So I'm going to find the critical number and as well the local maximum. I will let the slope of tangent to be 0. So after I've calculated, I find out the L should be 5 and as well the negative 5. But negative 5 will be rejected because dimensions cannot be negative. So that means step 8 to find the global maximum. So I put my critical number here and both of my endpoints, the domain closed interval endpoints into it. So after I compare this volume, I find out when L equals to 5, it will give me the largest volume of the rectangular box. So which means that this is my global maximum. So the question wants me to find dimensions of this rectangular box. So I know that L should be equal to 5 meters. So means that length and width should be 5 meters. So I just need the height of it. So I will just put 5 back to the equation here and to calculate the H. So after I do the calculation, I get the H will be approximately equals to 6.67 meters. So those are my dimensions of this rectangular box. So for the step 9, also the last step, I'm going to have my final conclusion here is when the length and width of the rectangular box are 5 meters and the height of it is 6.67 meters, These dimensions will maximize the volume of the rectangular box. So those are all my stats for this optimization questions, and thank you for listening.